Um, so in this lecture, we are going to talk about acidity and hardness. Here I put 3 cards here. The point is that we are going to like alkalinity, acidity, and hardness. They all describe the water. And we also have CO2 from the air. CO2 from the air, it can contribute to alkalinity and acidity and hardness. We also have the earth or the soil that will contribute like calcium, magnesium, and sodium, and potassium, and blah blah. Also to the water body. So they will contribute alkalinity and hardness to the water body. So this is the main point. So today we have 5 points. The first one is alkalinity has its rival. So we are going to talk about acidity, which is kind of like opposite to alkalinity. The next point is how to report acidity and alkalinity, and then it involves some of the calculations. The third one is hardness. So we are going to talk about hardness and its significance. And then we are going to talk about the source of hardness. And finally, we are going to report hardness. So I'm going to talk about the units of hardness. And this also involves some of the calculations. So first, let's just review what we discussed about alkalinity on Tuesday. So as we discussed before, for a water body that has relatively large pH, which is basic, we can add acid to determine its alkalinity. So we have a buffer zone because of very acidic water. We also have another buffer zone. And then we have a non-buffer zone. And then we will have buffer zone again and a non-buffer zone. And for the very acidic water, it is also a buffer zone. So it's good if you guys can remember like this picture. Oops, it's not this. And this is pH, and this is the log of the fraction of each species. And you guys remember what is this? This is carbonic acid or CO2. And in the middle, this is HCO3, and this is carbonate. And then we can also note that this is about 9, and this is about, let's say about 6. So if we can construct this plot in our mind, it will be helpful for understanding this whole unit. And again, this is a buffer zone, and this is a buffer zone. This is not a buffer zone. This is a buffer zone, and this is a buffer zone. And it's corresponding to the plot shown here. And we have castic alkalinity, phenolphthalein alkalinity, and total alkalinity. I think we did experiment together, these two, right, yesterday. By getting familiar with alkalinity, I'm going to talk about acidity. So this is alkaline. So we add acid here. This plot can also be understood as if we add base to here, and we can consider this as the volume of base added and this as 0. We can see that as we add base to a water that is acidic, as we add the volume of base, the pH will change like this. So it will be slow, fast, slow, fast, slow, and slow again. So when we add acid, it will go like this. But if we add base, it will go like this. And again, we have 2 equivalent points. These 2. And these 2 equivalent points corresponds to different acidity points. So here I want to introduce the concepts of acidity. I also list the concepts of alkalinity. So alkalinity is a measure of quantity of acid consumed to reach a certain point. But for acidity, it is a measure of the quantity of base consumed to reach a certain point. So I would say that they are symmetric, but their meaning are opposite. So it's kind of like these two foxes. So why do we care about acidity? Because it is related to corrosion of the pipes. We can see that this shows the mechanism of corrosion of the pipes. We can see we have the H plus here, and it shows that if we have more H plus in this reaction, then more Fe will be oxidized into this one. So if we have a water that has a small alkalinity or has acidity, or the water has relatively large alkalinity, then we can protect the pipe from corrosion. It is also related to water treatment, because some of the bacteria, they are only alive, or they can transfer the chemicals under certain pH. So we may adjust the pH based on both the alkalinity and acidity. Also, the water with acidity usually not harmful to humans, because like if we have CO2 in the water, we know that it is not too acidic, and so it is not harmful for us. But the waters with mineral acidity, they are not, they are unpalatable. So I think this tastes not good. Acidity is also related with acid rains, because the combustion of the fossil fuels with the impure fossil fuels, they will form sulfuric and nitric acid. So basically we have the sulfate and nitrate in the fossil fuel, and then when we burn this, we can generate SO2 and NOx. And in the atmosphere, we have oxygen and we have water, and then they will transform into sulfuric acid and nitric acid. And they will stay in the raindrop, and when it goes down to the lakes or the other water bodies, it will contribute acidity to the environment. Another source of acidity is, then let's talk about the source of acidity. So the main source of acidity is in natural water is CO2, because the natural water is in equilibrium with atmosphere, and we have CO2 in the atmosphere, and again this is 400 ppm in volume. And acidity, so here we need to remember the chemical reactions of this process. So this is the spell 1, 2, 3, and 4 in alkalinity lecture. So basically we have CO2 dissolved in the water. So CO2 become CO2AQ, and then CO2 can react with water to form carbonic acid, H2CO3, and then carbonic acid can dissociate into H+, and bicarbonate. Again, bicarbonate can dissociate into H+ plus carbonate. So it would be good for you guys to remember these reactions. And also, CO2 is an end product of aerobic and anaerobic bacteria of oxidation of organic matters. So the organic matter can be decomposed into CO2 and H2O. So some of the CO2 comes from the atmosphere, and some of the CO2 comes from the decomposition of the organic matters. We have some other sources except for CO2. The first one is mineral. Mineral acidity can be present in natural waters because we have some rocks, and these rocks may contain like Fe or like copper, and when they dissolved in the water, they can generate H+. For example, if we have Fe3+, it can react with water to form FeOH3, and this is solids, and H+. So basically, if you guys if you did the chemistry experiments in high school or something, if we dissolve this salt in the water, and then the solution is acidic, it presents more often in industrial waste and mining waste and the chemical waste because they may contain some of the metals. And the mining waste contains sulfates or sulfur that can be oxidized to sulfates by bacteria under aerobic conditions. So except for the metals, like the sulfur can also provide acidity because it will be oxidized. It will be oxidized into sulfuric acid. We can see the oxidizing state is 0, and this is +6. So far, do you guys have any questions? No? The next topic is how to measure acidity. So here I also list how to measure alkalinity, and then we can do the comparison. So first, so for alkalinity, we have caustic alkalinity, which represents very high pH. And we also have phenolphthalein alkalinity, which represents relatively neutral pH. And we have total alkalinity, which represents relatively acidic pH. Similarly, we have a mineral acidity, which represents relatively acidic pH. And we also have CO2 acidity, and this is also called phenolphthalein acidity. And then they kind of like a pair. Similarly, we have total acidity, which represents relatively basic pH, and this matches this one. So we have 3 alkalinity, and we also have 3 acidity. But in this class, alkalinity is more important than acidity. So many of the questions or problems will be related to alkalinity. Here is a summary of different acidities. So for mineral acidity, this is amount of OH required to titrate a solution to a pH of about 4.5. But according to different literature or different materials, this pH may change. But we just remember that this can represent a pH which is relatively acidic. And the methanol orange can be used as an indicator. So this is also called a methane orange acidity. And here shows the color of this methane orange. We can see the color is pretty. And here shows the chemical structure. And we also have CO2 acidity. And this is amount of OH minus required to titrate a solution to a pH of 8.3, and such a solution contains H2CO3 as a major component, and the titration consists in converting the carbonic acid into bicarbonate. So we remember that at pH equals to 8.3, the main species H is bicarbonate. So at this pH, we want to make sure we convert almost of the carbonic acid into the bicarbonate. And this is also called phenolphthalein alkalinity. And the last one is total phenolphthalein acidity. And the last one is total acidity. So this is also refers to the number of OH minus that must be added to raise the pH of the solution to this value. And again, This value may change by literature or materials, but generally it is around 11. Or to whatever pH is considered to represent a solution of sodium carbonate in water and the concentration of interest. So here, do you guys have any questions? No? Okay. The next question is like how to report acidity and alkalinity. So for alkalinity, we usually have two sets of units. The first one is milliequivalent per liter or equivalent per liter. It represents how much we need to convert the mass. So we need to convert the mass, like the milligram per liter, into milliequivalent per liter. And the equation is here. So CQ refers to the concentration in equivalent per liter, and it equals to the concentration of the chemical divided by the equivalent weight. So here, in this equation, the concentration is expressed in gram per liter instead of mole per liter. And the EW here refers to the equivalent weight in gram per equivalent. And EW can be calculated by this equation. So M here refers to the molecular weight in gram, and N here is the valence or ionic charge in equivalent per mole. And for example, we have calcium carbonate, because the calcium has two charges. So for calcium carbonate, N equals to 3. And similarly, we have magnesium, N also equals to 3. But for like the iron 3 plus, then N equals to 3 here. But the calcium carbonate is the most important one. So we need to remember for calcium carbonate, N equals to 2. Here shows an example. For calcium carbonate, N equals to 2. And the molecular weight is 100 grams per mole. So the equivalent weight is 50 because we use 100 divided by 2. So we got 50. This tells us that if we have 100 milligrams per liter of calcium carbonate in the water solution, it means that we have 0.1 mole per liter of calcium carbonate, and we have 0.2 equivalent calcium carbonate. Or intuitively, we can consider it as the calcium carbonate. It can combine 2H plus. Another unit for alkalinity is gram per liter or milligram per liter as calcium carbonate. So when we are reporting this unit, we need to include this part. So we cannot say gram per liter or milligram per liter. We need to say gram per liter as calcium carbonate. So calcium carbonate is part of the unit. So we can convert the equivalent as calcium carbonate using the equivalent weight of calcium carbonate. And so here shows the definition. The concentration as like gram per liter as calcium carbonate can be calculated by the equivalent times 50. And the 50 is the equivalent weight of calcium carbonate. So the key information is CQ here. And CQ can be calculated by this equation, and EW can be calculated by this equation. And the molecular weight and the charge can be found based on the chemical equation. So for these definitions, do you guys have any questions? No? Then let's look at an example. So the question is, the concentration of calcium in a water sample is 100 milligram per liter. Here I add a note. This means the concentration of the calcium, not the concentration of calcium carbonate. So when you guys are reading the problems, you may be cautious to this difference. And the question is, what is the concentration in milli equivalent per liter and milligram per liter as calcium carbonate? So in this question, we know that the balance or the charge of calcium is 2, so N equals 2. And then calcium atomic weight is 40. So its equivalent weight of calcium, not calcium carbonate. So it is 20. We use 40 divided by 2. And then we need to note that the equivalent weight of a substance is consistent because the atomic or molecular weights as ionic charge are constant. And then we can calculate the equivalent of calcium by using the 100 milligram per liter as given here, divided by the equivalent weight. So we can have 5. So the equivalent of calcium is 5 milli equivalent per liter. And then by knowing the CQ, we can calculate this. And again, we remember that the equivalent weight of calcium carbonate, not calcium, this is 50. So we can use the equivalence of calcium times the equivalent weight of calcium carbonate. So this is always this one, but this will change. So we use 5 times 50, and we can get this value. So for this problem, do you guys have any questions? No? Okay. The next one, we are going to talk about hardness. So here gives the definition of hardness. So the simple definition of water hardness is the amount of dissolved calcium and magnesium in the water. But the keyword is simple because we only consider calcium and magnesium in the water. And here shows the definition of total hardness. So basically, practically, because in the water, as we mentioned in last class, the main contribution is magnesium and calcium. And actually, this should be 2+. So the amount of calcium and magnesium can be considered as the total hardness. But technically, because we have different compositions of chemicals in water, so except for calcium and magnesium, we have like iron, we have manganese, and we have some other metal elements. So for the hardness, we can also divide it into 2 categories. The first one is permanent hardness and the temporal hardness. Temporal hardness is caused by the presence of dissolved bicarbonate minerals, and for example, calcium bicarbonate and magnesium carbonate, and it can be removed by boiling. So this is a key information. For example, we have calcium carbonate in the water, and when we boil the water, it will be composite into this one, and CO2 and water. So after boiling, we may have some precipitations as this one. So this type of the hardness is removed by boiling. And the next one is permanent hardness. So this hardness cannot be removed by boiling the water. For example, we may have chlorate calcium in the water, or like this one in the water. So they cannot be removed by boiling. So far, do you guys have any questions? Yes?
I'm confused. How come the first equation you gave us can't be removed by boiling, and how come the second ones can?
You mean this?
Yeah, like why can't they be removed?
Because they are more stable. We can say that the bicarbonate, it is relatively unstable. So when we heat this, it will be decomponent.
Okay.
Yes. Any more questions? Okay. So let's look at the hard water. I didn't mention one important concept is that the hardness only counts for the multivalent cations. So when we go back, we can see that we have sodium, we have potassium, but they did not count as hardness because they only have one charge. So we only count the hardness when the charge is greater or equals to 2. So the water hardness can be classified into different categories. And here I just randomly find 2 categories on the internet. We can see that they have different standards. So in the homework assignment, when you guys are describing a water hardness, you may refer to which standard you are going to use, you are using. So you need to use the reference to support your category. And then, like we have these numbers, we can see like we have different values. I will talk about the units of hardness later. And here I have a question. Do you guys know what is hardness of milk? If we consider the milk as a water, so I just did some research and we know the calcium content in the milk, like for the normal milk, it will be about 1,300 milligram per liter. So based on this, we can see that it is very hard. And here shows the water hardness of calcium as calcium carbonate in the United States. And I find this map, we can see that here in Maryland, the water is not quite hard, but in this region, the water is hard. So actually, I'm not quite familiar with the geography of the United States, but I'm just curious. Do you guys have any ideas about why this region has relatively hard water?
It's like the Rocky Mountains, right? The super mountains over there. Does that have anything to do with it?
Oh, so these regions have the Rocky Mountains?
Yeah.
Okay, yeah. And based on your answer, you know that the Rocky Mountain is a source of hardness. You want to say something?
I was going to say there's a lot of like canyons over there too, so there's a lot of erosion that probably pulls a lot of sediment.
You mean lot of canyon?
Canyons, like a lot of erosion.
Oh, yeah,
so
yeah,
that
yeah.
probably pulls sediment.
Yes.
Is this measuring in like drinking water, in surface water, in groundwater?
I think this is for the natural water.
Okay.
Yeah. Yeah, but I will double check, but in my memory it refers to the natural water. Yes. So let's talk about the significance of hardness. So hardness will also have some influence about our health. The WHO says that there does not appear to be any convincing evidence that the water hardness causes adverse health effects in humans, but this conclusion may be changed with time. And hardness is usually less aggressive and less likely to pick up harmful substances. And this is because if we have the hardness in water, like the harder water, usually contains more HCO2. So if we have more this one, we can see that the water is relatively neutral or neutral to basic. In the basic water, like the heavy metals, like this or this, they will be precipitated. So relatively basic water has relatively small amount of the heavy metals, which is better for us. And hard water can also attack dry skins and hairs. Because the calcium or the magnesium, they can have some chemical reactions with the oil in our skin or our hair. It also have some aesthetic effect. Like we know for the software, for the soft water, it is better for our clothes. So this is the new clothes, but if we wash the clothes, use the hard water very often, the clothes will become yellow or brown, which is not good. But if you tell me this is a new clothes, I would believe, because some new clothes have this color. So if we have soap, we can see that the calcium and the magnesium, they can precipitate with the soap, and so we will have the precipitation with some insoluble materials. And for the calcium and magnesium, I think nowadays we have the detergent, which is more soluble than water, so it will be more efficient when we are washing with the hard water. Here is an example. On the left is the soft water, and on the right is the hard water. If we have the same amount of soap in this two flasks, in these two bottles, and then we shake it, we can see that the bubble amounts are different. And according to our experience, we know that if a water has more bubbles, it means it's stronger to remove the dust or some other stuffs. We can see that it has more bubbles and it is more clear. But for the hard water, it only has a very small amount of bubbles, and it is very not clear, so it has some precipitations here. So basically, we know that for the organic matters, we will have like COOH or something like this one. So this is a hydroxyl functional group, which I will be talking about in the organic chemistry unit. But generally, this group can react with calcium and into C. Let me see. So two of these can react it with calcium, and then we have the calcium plus COO2, and this is usually precipitation. So many of the organic matters, organic acid will be precipitated by calcium ion. So we will have the precipitation here. Hardness is also related in our economy. So again, for washing clothes, soft water can let us to use less soap. And also, we also have the problem about scaling. So hardness reacts with certain anions present in the water to form scale. So basically, if we have boiling water and we also have the carbonate hardness, then we will have the precipitation. As I mentioned before, the general equation is we can decompose this into the calcium carbonate and water and CO2. So it usually happens in the boilers and stream and stream generation power plants, and we need to soft the water. So it's better to use the softened water. And we also have scaling in the hot water pipes, and the scaling are usually the calcium carbonate and magnesium hydroxide. And for the scaling in hot heaters, And again, because the carbonates are easier to remove. And here shows an example. I think this is a water heater. We can see that when it is new, it is this, but when we use it for many times, we will have the skinning on the surface of this tube because the surface is very hot. So it will form the precipitations on the surface of these tubes. And when we have the scaling on the tubes, because this scaling has very small heat conductivity, so the heat cannot be transferred to the water, so which we need to use more heat to increase the temperature of the water. The next one is about sources of hardness. And so for hardness, we can come from the carbonic acid and calcium and magnesium. So in the rainwater, it can capture CO2 from the atmosphere. And when the rainwater gets into the soil, because of the respiration, so the bacteria can convert the organic matter into CO2. So it can capture more CO2 here. So as mentioned here, in the upper layer of soil, we have air. So the CO2 can dissolve into the water. And we also have the bacteria, which can generate more CO2 in the soil. And the CO2 is in equilibrium with carbonic acid. And this carbonic acid can attack limestone and put the minerals into a solution. So the general equation is CO2 plus water, like plus CaCO3, and then we can convert it into a solution. So this is just a reverse reaction of the heat of the boiling water. We also have some hardness come from other metals. As I mentioned before, calcium and magnesium, they are the main source of hardness. But we still have some other minor contributions, like from iron or manganese. But we know that carbonic acid is not a strong acid, so it cannot dissolve these two. But under the anoxis condition, which means the condition there is no oxygen, the bacteria can use iron oxide, manganese oxides as an oxidizing agent. So generally, they can convert this one into this one and this one into this one. We know that for the iron dioxide, this is 3 plus, so it will be converted into 2 plus. So this is used as a oxidizing agent. And again, for this one, this is plus 4, and it will become 2 plus. And again, the oxidizing state decreases by the bacteria. And this one and this one, they are more soluble than iron with 3 plus or the manganese with 4 plus. So for this one, do you guys have any questions? No. The last one is about how to report hardness. And here is the hardness unit. And again, the units of hardness is similar to units of alkalinity. It is the as carbonate, like in milligram or in milliequivalents as calcium carbonate, so like this. And here I shows an example. So we have a sample from the groundwater. After the measurements, we know that the concentration of calcium is this, magnesium, iron, and sodium. And the question is, what is the total hardness in units of milligram per liter as calcium carbonate? In this case, we have 1, 2, 3, 4, 4 species. So we can do the calculation one by one. So for the first one, we can calculate calcium. And we know that its equivalent weight. The equivalent weight is 20 because the N equals to 2. So for calcium, N equals to 2. For magnesium, it's N also equals to 2. And for iron, N equals to 3 because it has 3 charges. And for sodium, N equals to 1 because it only has 1 charge. So we can calculate the equivalent weight of each one. And then we can calculate the equivalent concentration of calcium. So this is the concentration divided by the equivalent weight. So we can have the equivalent concentration. And then here shows the contribution of calcium to the hardness. It equals to the equivalent times 50 because this is calcium carbonate and the equivalent weight of calcium carbonate is 50. So we can have this value. And similarly, we can have magnesium like this, we can have iron like this, and sodium like this. So finally, I have a question. Is the total hardness equals to this one or equals to this one? Do any of you have any ideas? So this one equals to the sum of these 3. This one equals to the sum of these 4.
I think it's gonna be the first one because you said that N needs to be greater than or equal to 2, and for sodium, it's just 1 less.
Yes. So in this case, although we have the information of sodium, but the sodium N equals to 1, which is smaller than 2. So it does not contribute to total hardness. So we only use this 3. And for this one, do you guys have any questions? No? And that's it for today. So let's just review what we learned. Finally, we have the time to go through this. So the main source of acidity in natural water is, excuse me?
Carbon dioxide.
Yes, carbon dioxide in the atmosphere. And what can also cause acidity in natural water? In general, so that would be mining. Yeah, and yes, so like iron and like manganese, they can also contribute, but generally they come from mining. And also how to report acidity and alkalinity. The two common units for alkalinity is, yes, milligram per liter, right?
Yeah, millicube per liter.
Yeah, millicube per liter. And this one, is that correct? No, as, right, as calcium carbonate. And what is hardness? Is that important hardness in natural water mainly contributed by which two?
Magnesium and calcium.
Yes, calcium and magnesium. And where does hardness come from? Hardness of the water mainly based by I'm not sure why I use based.
The calcium, like the amount of calcium and the magnesium in the water.
Yes. So yeah, the main point is I also want to say that the main hardness can be calculated based by the concentration of calcium and the concentration of magnesium. But note that this usually refers to the natural water. If this is a wastewater or synthetic water, this may not be the case. And then how to report hardness. We also have 2 units. So again, this is equivalent per liter or milligram per liter, but as calcium carbonate. And finally, here are some ending notes. So I think yesterday we do the titration experiment, so please upload your data into the shared file. And for quiz 2, I think for the last 3 questions, like some of you have the questions in different order. So I have a plan. I posted on the announcement. So if you guys do not disagree with my plan, please send an email to me. We can discuss. And then for assignment 3 and quiz 3, it is due on next Wednesday. And for assignment 3, don't say this is a group assignment. So you guys can do them together with your group mates. Also, I want to say that please read the lab protocol because it will be helpful for your quiz and assignments. And Maria is grading assignment 3. So if you guys have any specific question related to the assignment 3, it would be better to ask to email Maria. And again, I will also try Zoom streaming and in person simultaneously on next Tuesday. I will find the optimized way to do this if I can figure that out. So that's it.